Hi everyone. In this video we are going to cover section 6.2 where we find areas between curves using integration. All right, so it's kind of just one step further than when we found the area under a curve. Now instead of just having a function f of x, we actually have two functions, f of x and g of x, and we want the area not from 1 down to the x-axis, but the area that is between the two curves. The process, though, is identical in that we divide our region up into n subintervals, all of these rectangles. And the height of the rectangle, instead of the function f of x and then that rectangle dropping down to the x-axis, right now our rectangle has a bottom that is defined by g of x. So we have a top and a bottom of our rectangle, right? But we still are going to find the height of that rectangle. But instead of just being the height defined by where the function is, it's the top of the rectangle minus the bottom of the rectangle, right? If the y coordinate here were 4 and the y coordinate here were 1, then the height of that rectangle would just be 3 units. Okay, so in our integral, now as you look down at the theorem, when we find the area between two curves, the key step is inside of our integral, we're going to subtract the two functions. So our bounds are from a to b, and then f of x minus g of x dx. We take the difference between f and g. And one other key part to this this theorem here is that f of x has to be greater than or equal to g of x. So it's going to be an important step to determine which function is on top, because we're always going to subtract the top of the rectangle, the top function, minus the bottom of the rectangle, the bottom function. All right, and that's what this symbol, or this inequality means. That's an important step that you're going to have to figure out. So let's look here at our first example, and in this one they don't give me the graph, so in some of these problems sketching the region is going to be a necessary step. So we're given r is bounded by the function f of x equals x plus 4, so let's draw that first. So that's just a linear function, y equals x plus 4, has a y-intercept up at 4, and a slope of 1 over 1. So I'm going to go 1, 2, 3, 4, and label that with a 4. And I'll do a couple tick marks. Actually, I'll have 4 tick marks on each of the other axes. 4, like that. I'll label my x-axis, my y-axis, and we're just getting a quick sketch of a graph. So here is my y-intercept, and again, up 1 over 1 for that linear function. And then I'll draw a line through my 3 points, decent line. That's f of x equals x plus 4. And then the other one, and it says bounded below by the graph of the function g of x equals 3 minus x over 2. So that one, it's written in the opposite order, but that one looks like, let's see, it has a slope of 3 and a negative 1/2 slope. Or it has a y-intercept of 3, excuse me, and a negative 1/2 slope. So down 1 over 2, there's a point, down 1 over 2, there's another point, up 1, back 2 if I wanted to go backwards, and we get a line that looks like that is decent. Oh, that point was not in a good spot. Should be a little bit higher there. Let's see, use my eraser. There. Okay, and that is my g of x function. G of x, 3 minus x over 2. And they tell me that we're looking between 1 and 1, 2, 3, 4. We're looking between 1 and 4. So then the region R in this case that we're talking about, what is bounded by, meaning between those two functions? Well, that's this red region that I am marking up here. Kind of looks like a trapezoid. Actually, it is a trapezoidal region because those are straight lines, those two functions. But instead of getting the area of a trapezoid, although you could use the formula for area of a trapezoid here, and it would be correct, we can also use calculus to make it way more fun. So we're going to take, to find our area, we're going to set up the integral from a to b, f of x minus g of x dx. And I know that it's f of x because my green line is the one on top. If the g of x function were on top, then that would need to be first. Okay, so this is the integral from 1 to 4. Those are the bounds that were given for this region. And then our f of x function is x plus 4 minus our g of x function is 3 minus x over 2. And then dx. This one, I think it would be best to simplify first because we're just going to combine some like terms, giving us fewer terms to integrate. I'm going to write the integral sign again. I'm going to write dx again. And then let's see, I have 4 here minus 3 there. 4 minus 3 is 1. And then I have an x there minus a negative x over 2. So that's x plus half an x, or that would be, when you add them together, 3 halves, 3.5, or 1.5 x. 1 plus a half is 1.5, which is 3 over 2. Okay, and that one was positive. Yes, it was. All right, and again, this is one where if your fraction skills aren't up to snuff, that's okay. Just use your calculator. Now we're ready to take our antiderivative. So I'm not going to write the integral sign, and I'm not going to write the dx this time. So the antiderivative of 3 halves x is 3 halves times x squared over 2, plus the integral of 1 is x. And all of that gets evaluated over the bounds from 1 to 4. Let's go this way. I have my second example down there. So let's see. When we plug in our top bound, we're going to get, let's see, I'll rewrite that 3 halves, and the x squared over 2 is 3 fourths times 4 squared plus 4. So that's the top bound substituted in, minus 3 fourths times 1 squared plus 1. The first bracket simplifies to 16. The second bracket is a fraction. It gives you 7 quarters. 16 minus 7 fourths is 57 over 4. That would be one where it would be perfectly reasonable to leave it in decimal form also. All right, so let's look now at our next example. And in this one, we have a parabola and a line. Okay, so again, I'm going to sketch the region. Again, pause if you want to read through it and maybe even try sketching it on your own. But I'm going to sketch this region. And if you have trouble with the graphing, you could always use a website to punch it into. Wolfram Alpha is a good website. You can just type the equation in, and they'll give you a nice looking graph. So for mine, the 9 minus x over 2, that squared, is up here at 9. It intersects the y-axis, and then it's a downward facing or downward opening parabola like that, and it intersects the x-axis at 6. And again, I could do the work to show that, but I'm not in this example. All right, and then the g of x function, that's a line. Y-intercept is up at 6, and the slope is -1. So let me add a 6 right about there. And what that line ends up doing is it goes here, and it comes down and crosses the x-axis at 6. If you have a graphing calculator at home, you could certainly use that also to look at the graphs of these. Sketching the graph is important because in this one, I'm not given bounds. Okay, we're not told that right off the bat. Okay, and so I'm going to need to figure out, well, I can see that that is a 6, but I'm going to need to figure out what x value is right there. Is it -1, -2, -3? Well, we have to do some work to figure that out. Okay, but as it stands right now, I can set up most of this integral given the picture that I have. Our area here is the integral. I don't know my a to b. Technically, I know my b. I know the 6. Okay, but I'm going to leave the bounds off for right now. And the top function is the parabola. So 9 minus x over 2, oops, that's a 2, squared is the equation of my parabola. That's the top function. So if I were to draw that rectangle in the region here, right, the top of that rectangle is defined by the parabola, and the bottom is defined by the line. So then minus the equation of the line is 6 minus x, and excuse me, and then dx. Okay, so there's our integral that we need to evaluate, but now I want to know what the two bounds are. And if sketching it is challenging, what we can also do to figure out the bounds is to set these two equations equal to each other, because I want to know when f of x and g of x are equal. That's going to give me this point and this point right there, the x coordinates. So I'm going to set up 9 minus x over 2 squared is equal to 6 minus x, and solve that quadratic equation. That's going to give me my 2 points of intersection. Okay, and sometimes we need to do that if we're not given, like in the previous example, we were given the interval right off the bat. All right, so if you do the algebra here, let's see what we get. I'm going to square that, the x term. So this is x squared over 4, 6 minus x. Now I'm going to subtract the 6 from both sides because that'll make one fewer term. X squared over 4 equals negative x. Now I don't like the x squared over 4, so I'm going to multiply through everything by 4. 12 minus x squared is equal to negative 4x. All right, and now I'm going to bring everything over to the right-hand side so that my x squared term is positive. So I'm going to add that and subtract that. X squared minus 4x minus 12 is 0. And then that factors into x minus 6 times x plus 2. And the solutions, x equals 6, x equals negative 2. Now, I went through that at a pretty fast pace. Go back and rewatch it if you need to. It's a prior, content that we need to use here. If it's something that you struggle with, get some help in it, okay? But it's necessary in order to answer this question, in order to figure out the x bounds for my integral. So coming back up to my integral, it's negative 2 up to 6 for my bounds. I'm not going to go through all of the evaluating for this integral. I would square this and write it as x squared over 4, and then combine the 9 and the negative 6. So maybe I'll write out that one more step and then the answer. So this is negative 2 up to 6. 9 minus 6 is 3, minus x squared over 4 plus x dx. Now you're ready to take the antiderivative and go through all of the calculus steps. Let me do one more step. What the heck? So this is 3x minus x cubed over 12 plus x squared over 2. All of that is evaluated from negative 2 up to 6. And when all said and done with this one, you should get 64 thirds for the area of that region. The area of this guy here is 64 over 3 square units. In our next example, we are given the graph, so we're fortunate enough to be given the graph of f of x equals x squared, g of x equals 2 minus x, and here's the region that we're talking about where we need the area of. And figure 6.7 below it says 2 integrals are required to calculate the area of this region. So why is that? Why do we need 2 integrals here? Well, if you think about that rectangle that we divide our region up into, right? As those rectangular cross-section slices go through our region, right? Here, the top of the rectangle is the parabola, and the bottom is the x-axis. And then once we get over here, the top of the rectangle is the line, and the bottom is the x-axis. And it all changes at 1. So the reason that we need 2 integrals is because what defines our region changes as we move from 0 up to 2. All right, so the way that these 2 integrals look is, first we have the integral from 0 to 1 of the parabola, x squared dx. And notice there's no bottom. These go down to the x-axis, so there's no minus some other function. And then we're going to add to that the integral from 1 to 2 of 2 minus x dx. And again, there's nothing being subtracted there because our region goes down to the x-axis. All right, so that's the setup for this next example. And then you take your antiderivatives. The first one, x squared becomes x cubed over 3, evaluated from 0 to 1. And then 2x minus x squared over 2, evaluated from 1 to 2. So the only thing I get out of my first integral is 1/3 minus 0, plus 2 times 2 is 4, minus 2 squared is 4 over 2 is 2, so that's the top bound, minus the bottom bound, 2 times 1 is 2, 1 squared over 2 is a half. All right, and then when you simplify all of that arithmetic, I believe you should be left with equals 5 over 6. And that's the answer to this one. Okay, the last key topic in this section is defining our region with respect to the y-axis. So this is a little bit different. Sometimes, depending on the setup for a problem, it is better, more efficient, will save time, or possibly be easier if we set up our region with respect to the y-axis. If it looks confusing looking at these two pictures, just tilt your head slightly to the right and it'll all look normal. But the way that this region is given, right, where I have my red curve U and my blue curve V, right, the top and the bottom of the region are not defined by the functions. The top and the bottom of the region are defined by these two values on the y-axis. And so if I did my vertical rectangle, right, how would that make any sense in terms of the top of the in terms of finding the area of that rectangle efficiently? And the answer is it wouldn't. Okay, so in some problems, and I'll always tell you directly when you should write it with respect to the y-axis. It'll be clear in the setup. But in some of these problems, we are going to divide our region into rectangles oriented so that they are perpendicular to the y-axis, and we add those rectangles up, moving up the y-axis. And we're not actually going to add the rectangles. We're going to do calculus and take antiderivatives, but conceptually, that's what we are doing. We're adding up rectangles vertically, and the height is still going to be determined by the function, but now it's the function in terms of y, and what that means is solve for x equals. Write it with as x equals instead of y equals. Okay, and then the bounds for these integrals are going to be bounds up along the y-axis. Okay, so let's look at what our formula looks like here, and it's basically the exact same with different letters. We still have to determine what our top function is. Right, the top is going to be the higher up on the x-axis now, and I'll explain that when we get to an example. Okay, but we're still going to set this up. Our bounds, we have to figure out our bounds, and then top function in terms of y minus bottom function in terms of y dy. And these were all supposed to be arrows, but it didn't work out so well. There we go. That's better. All right, so same concept, just shifting our heads 90 degrees kind of. And the example that we're going to do is actually one that we've already answered. We'll just now orient ourselves a little bit differently. So we're looking at the same region as the previous example, okay? But now we are going to integrate with respect to y. So what I'm going to do is I'm going to draw my rectangle inside of that region. And I'm going to do that in most of the examples and most of the problems moving forward, because it helps to visually see and kind of think about how those rectangular cross sections add up through the region. So I'm going to draw that in there. Maybe I'll color it in a little bit. There we go. And what we need to do, all right, is we need to, well, let me first rewrite the formula. How about that? A equals the integral from, it was c to d, and then it went u of y minus v of y, and then dy. So I need my top function in terms of y, my bottom function in terms of y, and then the bounds going up the y-axis. Let's start with the bounds. So going up the y-axis, we can hopefully see that that blue region, that rectangle, the rectangle inside of the blue region, the first one will be down here at y equals 0, and then they will add up through the region until we get up to y equals 1. So our bounds, that's first, are from 0 to 1. All right, piece of cake. No, not really. That's the first step. All right, now, which is the top of the region, which is the bottom of the region? Okay, when we talk top and bottom, here's where the bigger numbers are, here's where the smaller numbers are. So over here is I'm writing sideways here, that's the top of the region. So the top of my rectangle is the blue line, and it's g of x, or y, equals 2 minus x. So we'll do a little bit of algebra, add x to both sides, subtract y from both sides, and we get our region. Now we have a function in terms of y. Okay, so the top of the region is 2 minus y, minus then the bottom of the region is y equals x squared, f of x equals x squared, right? So I can write that as y equals x squared. To solve that for x, we use the square root property. X is equal to the square root of y, and that is the bottom of the region as a function of y. And when we put that into our integral, we're going to write it as y to the 1/2 power, because we know that we're going to need to use the power rule to take the antiderivative. All right, so that's the setup. So we solve our equations for x equals, and we figure out our bounds going up the y-axis. All right, now our integral of 2 is 2y. Normally it's 2x, but now we're in terms of the variable y, so that went here, minus y squared over 2, and then minus y to the 3/2 over 3/2. And that the first 3/2 is an exponent, in case it didn't look like it. That's from 0 to 1. Let me give myself some more space over here. All right, the nice thing about the 0 there, when I plug 0 in, for the bottom bound, everything is going to be just 0. So all we need to really worry about is our top bound. So this is 2 times 1 minus 1 squared is 1 over 2, minus that 2/3 flips up. Well, the 3/2 flips up as a 2/3, times 1 to the 3/2, which again is 1. And then I'll write down minus 0, representing the bottom bound, plugging into each of the 3 terms. And then the arithmetic there all simplifies to 5 over 6, which is the exact same as we got in the previous example. So in the other one, it wasn't terrible, but we needed 2 separate integrals, although they weren't terrible to evaluate. In this one, we plugged it all into one integral, probably about the same amount of work in both cases, but there are certainly other scenarios where integrating in terms of y eliminates a lot of the work that integrating in terms of x would cause. Okay, so just connecting it again, finally, this 5 over 6 represents the area of this kind of triangle. Not exactly a triangle, but it's kind of a triangle. All right, so that is the end of the video. Thank you very much for watching. Start on your homework. Please let me know if you run into problems. Have a wonderful day.